Hello AP Chem students and welcome to topic 6.9, Hess's Law. We have two learning objectives today. The first one is 6.9.a, represent a chemical or physical process as a sequence of steps. And 6.9.b, explain the relationship between the enthalpy of a chemical or physical process and the sum of the enthalpies of the individual steps. So let's look at it. If it will let me advance my slides. There we go. As we first explored in kinetics, many times a process can be broken down into several smaller steps that occur in a series. This means that we can take a series of reactions, each with their own energy change, and combine them so that they give one reaction overall. We also then combine their enthalpy values to give the enthalpy for the overall reaction, which is an application of Hess's law. So Hess's law says that the total enthalpy change of a reaction is independent of the sequence of steps. In other words, it doesn't matter how you get there, it's just the kind of start and end that matters. So this is an application of the first law of thermodynamics. Because energy is conserved and each step transfers thermal energy to and from the surroundings, the total energy transferred overall is equal to the sum of all the energy transfers. So you can look at this graphic up here. We can go directly from A to B and get an enthalpy value there. Or we could go from A through C to B, or A through D through E and back to B, and it doesn't matter. The overall enthalpy change will be the same for all three of these processes. So let's think about the rules of Hess's law. So first of all, the steps must add up to give the overall reaction. If the steps don't sum stoichiometrically to give the reaction, then you don't have a series of steps that matches your beginning and end, and it's not applicable. Number two, if you reverse an equation so that the reactants become the products and the products become the reactants, you flip the sign of the delta H value, and that should make sense to you. You've just inverted it. If you multiply an equation by an integer, you also multiply the delta H value by that same factor. Okay, so in this case, you can see we've got root 1, we've got root 2. Root 1 is equal to root 2. So you can go either way here. So then delta H of 1 would be equal to something plus delta H2, and then you can rearrange and solve for that. This graphic is not actually as helpful as I originally was thinking it would be when I put it in the slide here, but you can see that if you don't know the path from A plus B plus C gives you X plus Y plus C, you can actually solve to find it if you know the two paths independently. So let's look at a practice question. So calculate the value of delta H for the following reaction given the data that follows. And so you have the overall reaction, and that's what you're trying to find the delta H for. And then you have a series of steps, each with their independent enthalpy values. And so if you would like to try this on your own first, please go ahead and pause it because I'm about to go over the answer. Okay, so I've got some highlighting going on here, which I think is very helpful. Now, again, on the AP exam, you're going to be taking this exam on a computer, and so you will have scratch paper. Definitely, you'll be having paper that you'll write your answers on for the free response. Not sure about multiple choice, but I do believe there are highlighting tools on the test software, so you could highlight to kind of help yourself here. So let me show you what that looks like. So I'm just going to start with the CO. So here's the CO that's present in our reactants for our overall reaction. And so we need to find it in one of the steps below. And so there it is. And it is exactly the same. The coefficient is correct and it's in the correct location. So we would like to keep that delta H value as is. So let's keep moving through the reaction here. Next, we encounter our 4H2. So I can find H2 in the second reaction, but it has a coefficient of 2. So to solve this, we're going to multiply this whole reaction by 2, which means that we're also going to multiply our delta H value by 2. And so when I do that, I get a negative 1144. Now, I like to go ahead and do the math as I'm working through the steps, but for each individual delta H. So I will multiply it by 2, but I'm not going to do anything else with it at this moment. Then we've got our ethanol here, and let's find our ethanol, and there it is in the third reaction. But in the third reaction, it's a reactant, and in our overall reaction, we need it to be a product, which means we need to flip it. So sometimes I find it more helpful to rewrite, which I'm going to do for you today. So there it is rewritten, and there's your ethanol as a product. So when we do that, we're going to change the sign of the delta H. So that delta H is going to change from being negative to being positive. So if we're going to now look at the water, which we can see here we have in our products, there it is. Okay. It might initially seem that we have a problem because we need one water to be left in the products, and it looks like we have two waters here. But I want to remind you that we multiplied that whole second reaction by 2. And so this is actually 4 waters, and that cancels with the 3 waters that we have in our reactants now, leaving us the 1 water, which is what we need in our overall reaction. So it looks as if things are going to work out. So let's do a final check and make sure that everything cancels that we don't need. Oh, so there was that water there. Okay, so then that O2 and that O2 sum together to give 1. And then remember, we multiplied this by 2. So this is 1, 2, 3. That cancels with that one down there, which is great. And then I've got my 2 CO2, and that cancels with my 2 CO2. So I should be all good to go. So now all I need to do is come over to my delta H values and sum them. And I get my final answer of negative 340 kilojoules. So that's how we do a Hess's law problem. Now, there is a particular application of Hess's law to something called the Born-Haber cycle, which I just want to make you aware of. So we can talk about the energy change in the formation of an ionic compound, and the process of applying steps to model that is called the Born-Haber cycle. And we usually see it represented as an energy diagram like this below. So where you have kind of multiple steps and you have things happening between, like, starting with elements, and then electrons come in to the situation here, and then you end up with the formation of the solid overall. So we're normally used to seeing it just, one element plus the second element gives the solid overall, but actually it's a little bit more complex here. And so when we examine the process by which the actual subatomic particles are rearranging and things like that, then that overall process is called the Born-Haber cycle. So then this is an application of Hess's law to show the formation of an ionic compound from a metal and a nonmetal. It nicely shows that bonds form when the collection of atoms is more stable or has a lower energy than the individual atoms. And then if we examine the reverse of that process, that gives us a value for something called the lattice energy of a crystalline solid. So you can see that here. This is probably more complex than you're going to see on the AP exam, but if you do see one of these diagrams like this, it's really just an application of Hess's law. Okay, so what should I be able to do with this? First of all, manipulate the steps in a reaction sequence to match the overall process and calculate the resulting delta H. Remember that if we inverse the reaction, we flip the sign. If we multiply the reaction by a value, we would also multiply the delta H by that same value. And then all the steps need to sum to give the overall reaction, and then you correspondingly sum the delta H values. And then use the results of Hess's law to justify the overall sign of a process, even if the component steps have a different sign. Because remember that once you sum them all together, you might have some endothermic processes that are part of a reaction mechanism, but that mechanism overall could still be exothermic. So it's important to remember that as well. And that is it. So that, I believe, brings us to the end of Unit 6 in thermochemistry. We will come back to principles of thermodynamics in Unit 9 at the end of the course. But from here, we'll be moving on to Unit 7, which is equilibrium, and I'll see you then.